Hello everyone, welcome to Engineering Explained channel. In this session, I am going to take Basic Thermodynamics Model 1 Lecture 10. That is, I am going to take Thermodynamic Processes. I am going to take the derivation for the work done expression for different processes. And the different thermodynamic processes are isobaric or constant pressure process, isochoric or constant volume process, isothermal or constant temperature process, isentropic or adiabatic process, and polytropic process. For all these processes, I'm going to take the work done expression. First, I will take isobaric or constant pressure process. Here, during the process, when the changes the state 1 to the state 2 during that process, the pressure will be remains constant, and by maintaining the pressure constant, the work done we have to derive for that one. Here the expression we will take by considering the PV diagram, the pressure volume diagram, and for that pressure volume diagram, the state or a condition of a system changes from the 1 to 2, and there the process is taking place. During that time, the pressure will be remains constant and the volume changes. The volume changes from the V1 to V2. And the area under the curve will be the work done for the this process. And that we can take here, work done equal to area under the curve 1 to 2. And that is given by W1 to 2 is equal to integration of 1 to 2 P dV. The pressure change in volume, the PDV work, and that is equal to P, uh, and dV will be the integration of dV will be V, and within the range of 1 to 2, and that can be given as W1 to 2 is equal to the pressure is remains constant, and V2 minus V1 is the work done expression for the constant pressure process. And next I will take the isochoric or a constant volume process, and during that process the volume will be maintained constant, volume will be remains constant, but the pressure changes, and that expression will take the PV diagram, the pressure volume diagram. At the state 1 the pressure will be P1, and at the state 2 pressure is P2, and this is changing, and the volume will be remains constant, the volume is remains constant, the V1 equal to V2 equal to V0, that is the initial volume, the V is remains constant, and we'll take the work done expression for this. The work done is given by area under the curve 1 to 2, and there is no area under this curve. Okay, the area curve is like this, there is no area under this curve. Therefore, here the will take that is again by taking the integration of PDV work, W1 to 2 is equal to 1 to 2 integration of PDV, that can be taken as a P into V of V 1 to 2, and again the this W1 to 2 is written as the P V2 minus V1. Okay, then V2 minus V1, what it is there? Okay, that is the V2 equal to the V1, and that will be becomes 0. That is, since V1 equal to V2, the work done during the constant volume process is 0. Always you should mention that one. The work done will be remains 0 during the constant volume process. Next is the isothermal or constant temperature process. The PV diagram for constant temperature process is that this one, and here the state 1 to state 2 changing the state by the process curve like this, where the PV will be remains constant, where the PV is equal to mRT. We are going to take m is constant mass, that is a constant, R is a gas constant, that also taken as a constant, and T is a constant. Therefore, the PV will remains constant here. Then we can write the P1 V1 is equal to P2 V2. For this will be remains constant for the process. And here the pressure is changing from the P1 to P2, volume is changing from the V1 to V2. Then work done will take here, work done equal to area under the curve 1 to 2. Then W1 to 2 is equal to 1 to 2 PDV. Then for an isothermal process, how you can write isothermal process. We know that the PV equal to P1 V1 equal to P2 V2 is equal to constant C. Then the P can be written as the P is taken as the P1 V1 by phi. That is a P1 V1 by phi. And this P value, if you substitute in this work done expression, then after the integration, we are going to get the work done. And after substituting, we are going to get W122 is equal to integration upon to 2 P1 V1 by phi into dV. Okay, then P1 V1 will be remains constant, that can be taken outside of the integration, and 1 by phi will be integrated, and that will be P1 V1 1 by phi integration will be the ln phi 1 to 2. Then this can be written as P1 V1 ln V2 minus half V1. Then this can be written P1 V1 equal to ln V2 minus half ln V1. Ln V2 ln V1 will be ln V2 by V1. Then W122 that can be written as P1 V1 ln V2 by V1, or in terms of the pressure we can express P1 V1 ln P1 by P2, where V2 by V1 is equal to P1 by P2. Like this, the expression, work done expression for isothermal or constant temperature process is the P1 V1 ln P2 by P1, or P1 V1 ln P1 by P2. Further moving, isentropic or adiabatic process. This is the PV diagram for the adiabatic process, where the curve is for the PV raised to gamma equal to C, where gamma is the adiabatic index. And at state 1, the pressure will be P1, at state 2, volume V1, and at state 2, pressure P2 and volume V2. Then for this, the work done we can take work done equal to area under the curve 1 to 2. Then W1 to 2 is equal to integration upon to 2 PdV. Then for an adiabatic process, PV raised to gamma equal to P1 V1 raised to gamma, P2 V2 raised to gamma is equal to constant, where gamma is equal to 1.4, that is adiabatic index. Then in this expression, the P is taken from this relation for the adiabatic process and substituted in the work done expression and integrated. Then here from this one, we are going to take the P equal to P1 V1 raised to gamma by P raised to gamma. This, if you substitute in this equation, we are going to get W1 to 2 is equal to integration of 1 to 2, that is P1 V1 raised to gamma by V raised to gamma into dV. Then this integration, how we can take, that is a P1 V1 raised to gamma, this is taken as the constant outside, integration of 1 to 2, this V raised to minus gamma. If you take this V raised to gamma in the numerator, we are going to get V raised to minus gamma dV. Then this P1 V1 raised to gamma is outside, then integration of V raised to minus gamma equal to V raised to minus gamma plus 1 by minus gamma plus 1, that is from 1 to 2 range. Then P1 V1 raised to gamma outside only, then the same V raised to minus gamma plus 1 by minus gamma plus 1, 1 to 2, that expression is continued. Then P1 V1 raised to gamma inside, this is V2 raised to minus gamma plus 1 minus of V1 raised to minus gamma plus 1 by minus gamma plus 1. Then this, if you this P1 V1 raised to gamma, if you take inside and multiply with these two terms, then we are going to get, here V2 is there, then this P1 V1 raised to gamma equal to P2 V2 raised to gamma, then this relation we know, then therefore for the first term we will multiply with the P2 V2 raised to gamma. Okay, the both that is equal to the P1 V1 raised to gamma. Then that multiplication for the first term we are going to take, that is the somewhat different, that we should know it. P2 V2 raised to gamma into V2 raised to minus gamma plus 1 for this first term. V2 raised to minus gamma plus 1, and this P1 V1 raised to gamma, instead of that we will multiply with a P2 V2 raised to gamma, because P1 V1 raised to gamma equal to P2 V2 raised to gamma, minus of, again for this we will multiply P1 V1 raised to gamma only, P1 V1 raised to gamma into V1 raised to minus gamma plus 1 by this we can rearrange it 1 minus of gamma. 1 minus of gamma we can write. Then here the P2 and V2 raised to this is plus gamma minus of gamma plus 1. And similarly here we will take minus P1 into V1 raised to gamma, this gamma minus of gamma plus 1. Therefore, these from these two terms, the gamma gamma get cancels. The gamma gamma, the minus and plus, those will be get cancels. Therefore, P2 V2 raised to 1 minus of P1 V1 raised to 1 will be remains, and in the denominator 1 minus of gamma will be there. Then we can write P2 V2 minus of P1 V1 by 1 minus gamma, or this we can write as a W122 is equal to this we can rearrange P1 V1 first we will take and minus of P2 V2, and in the denominator also we will interchange. Instead of writing 1 minus gamma, gamma minus 1 will take because gamma is a 1.4. This is the work done expression for the adiabatic or isentropic process. And further moving, next one is a polytropic process. In the polytropic process, where the whatever this curve is there, okay, that is according to the polytropic index n, and that is PV diagram on that we can take the change of states from 1 to 2, where at state 1 the pressure is P1, volume is V1. At state 2, pressure is P2 and volume is V2. And this curve is according to the PV raised to n equal to constant. That we can write P1 V1 raised to n equal to P2 V2 n raised to n equal to constant. We can write. Then work done for this polytropic process we can take here work done equal to area under the curve 1 to 2. W1 to 2 equal to integration of 1 to 2 PdV. Then for polytropic process Pv raised to n equal to P1 V1 raised to n, that is equal to P2 V2 raised to n equal to constant C. Then where n is polytropic index. Then from these two we can write P equal to P1 V1 raised to gamma n by V raised to n. Then this P, if you substitute in the above equation, that's the work done equation, W1 to 2 is equal to integration of 1 to 2 P1 V1 raised to n by V raised to n into dV. Then P1 V1 raised to n is constant, that is taken outside, and within the integration 1 to 2, and this V raised to n is taken in the numerator, that will become say V raised to minus n into dV. Then after the integration we are going to take the P1 V1 raised to n will be again outside, and this V raised to minus n will becomes the after the integration V raised to minus n plus 1 by minus n plus 1 from the range 1 to 2. Then again the same equation we can carry P1 V1 raised to n V raised to minus n plus 1 by minus n plus 1 1 to 2 range. Then here the P1 V1 raised to n will be outside only. Then if you substitute this 2 here, the V2 raised to minus n plus 1 minus of V1 raised to minus n plus 1 by minus n plus 1. Then again for the first term we will multiply with this term. Instead of multiplying with the P1 V1 raised to n, we will multiply with the P2 V2 raised to n, because P1 V1 raised to n equal to P2 V2 raised to n. Then that multiplication here will take the P2 V2 raised to n into V2 raised to minus n plus 1, and for the second term the same value will multiply because here V1 is there, minus P1 V1 raised to n into V1 raised to minus n plus 1. By this we can rearrange 1 minus of n we can write. Then after this the index what are there, those for the V2, if you take that index, that is a P2 V2 raised to n, that is n minus of n plus 1. Okay, that this is minus n plus minus n plus n plus of 1, again minus of P1 V1 raised to minus n plus n plus of 1, and this minus n and plus n get cancels from these two terms. Then only P2 V2 raised to 1 will remains, and here the P1 V1 raised to 1 will be remains, that we can write P2 V2 minus of P1 V1, and in the new denominator 1 minus of En will be there. This we can write as a W1 to 2 is equal to this term, second term will take first in the interchange in the numerator and denominator also, that we can write P1 V1 minus of P2 V2 by En minus 1. This is the work done expression for the polytropic process. In the polytropic process, the N is varying from the 0 to the higher numbers. When N equal to 0, it will become say constant pressure process. Then here the vertical range, the N equal to infinity. Okay, for that constant volume process. Within that, all these are quasi-static process, and where N is varying from the 1, 2, 3, 4 like that, and the any value it may takes. Like this, the work done expression for all this, the thermodynamic process I have taken, and how those are derived I have explained here. Thanks for watching. If you like, share, subscribe and comment.